Hi everyone, and welcome to sections 4.2 and 4.3. So in this combo of sections, which are very closely related, we're going to be using derivatives to learn about functions. So we've already done this a little bit, right? We've already done some work connecting derivatives and the way functions behave back in chapter 3. And so just to kind of remind you of where we've been. So far, we talked some about how if I have a function f, we'll just do f of x, then I know a couple things. Like this is going to be increasing whenever the derivative is positive. And then on the flip side of that, it's going to be decreasing whenever the derivative is less than 0. Okay, so we saw a couple of those connections and talked about them a little bit, had you talk about them in homework, just to kind of try to keep nailing it home. But we can do more than that. And it's going to just be a process that you have to get comfortable with doing. But if you've taken the time to really think through these ideas and connections, the ones with concavity too, this you're just going to be like, oh, this is a natural next step of that, and it totally makes sense that we would do these things. But if you are, still unsure, thinking through these ideas with a function, its derivative, its second derivative, concavity, then this is just going to bring that back. So it's very important we really try getting these ideas in our head. Function, what does its derivative tell us? What's the second derivative tell us? Okay, so we already have talked about when I go up, derivative says this. When I go down, derivative says this. So we could do a little bit more than that, come straight from it. And what we're going to be doing first is talking about maximum and minimums for our function, because the derivative can help us find those too. So there's a couple definitions here that are a little more technical, but they just are what you would think they are. We have absolute maximum and mins, which means this absolute maximum, this is the highest y value my function will hit over its entire domain. This is the tippity top. Okay, so an absolute maximum, I'm going to have two pictures here. So there's going to be a function like this. The absolute maximum, and just pretend the function's only defined where I drew it. The absolute maximum will be here. It's this tippity topmost point. Okay. On the other hand, though, we do have local maximums. What's a local maximum? So a local maximum is a top. It's a highest point, highest in y value, largest, right? But it doesn't necessarily have to be the tippity top of your function for the whole range. Just locally, and the word here is near. When x is near this little c, so you've seen this maybe a couple times before, near being there's some open interval. You go left a little, you go right a little bit. If you're standing here, this is you, right? And you look left and you look right, and for just a little bit, you don't have to go very far. Look a little bit left, a little bit right, and say, am I at the top? That's a local maximum. Now, if you look far enough to the right, you're going to see, ooh, there's another mountain there that's even taller. That's okay. It's a local maximum. In my little local area, I'm a max. This one up here is an absolute max. There's a little kind of double thing here you might think about. Go to the definition. A local maximum value of f is a number, f of c, holy moly, is a local max value of f if it's bigger than all the other function values near c. So technically, this is also a local max. It's a local max because, what did we say? Put yourself here, look left a little, look right a little, I'm the biggest. It just also happens to be the absolute maximum because it's the biggest everywhere. It's the tallest mountain here. So absolute max, the tallest mountain in the whole range of mountains of your function. The local max, well, there's little mini mountains here that you could still be at the top of this mountain. It's not necessarily the tallest mountain, but in your little area, it's the highest point. Same thing with absolute mins, right? So we'll just redraw this picture. We could just adjust this one, but we'll redraw it. So maybe you've got something like this. It goes down here, and then maybe it goes down like this more. Okay, so for this function, we've got kind of some key points we can think about here. The local minimum, we'll do that in green. Green, I just used green. How about blue? The local minimum here. So I'm standing at this point. There I am. And I'm at the bottom. I look left, I look right. Every other point is higher up than this blue dot here, right? So everything else is higher. But that's only locally near this value C, which is an X value. There's actually a point, the absolute minimum, right? We'll do that in gray. The absolute minimum here is just the most minimum point of everything, right? It's the point with the F value that is smallest. So that would be right here. So we've got local maxes, local mins, absolute maxes, absolute mins. So why am I, probably going way too long about these things? Well, it just so happens, right? There's two big theorems here. We're going to start with Fermat's theorem here, just because it's going along with things, I think the first thing you might think about. If a function has a local max or min at C, and if the derivative exists, we'll talk about this a little bit, then the derivative has to be 0. Okay, so let's break this down. If a function has a local maximum or min somewhere, just somewhere, you got your function, here's C, and around C it looks like this. Okay, so that looks like it's a local minimum. If the derivative exists, which the way I drew this seems like it does, we're just going to assume it does, then the tangent line here has to have a slope of 0. And remember, that's just the derivative. So why do I care about that? Well, with some of these things, you can think, what about going backwards? Okay, if there's a local max or min and the derivative exists, then it's got to be 0. So if I have a function, I take the derivative and I get 0 somewhere, oh, I could have a max or a min. All right, that's the idea. I can try to go backwards here. And so this gives us like an actual, real way to find local maxes and mins. We take the derivative, we set it equal to 0, we go find a C that works here, and we may have found a local maximum or minimum. Okay? And we can do that on the whole function. You take the derivative of the whole function, right? And then we can try to solve for the possible solutions to this. Now, what's the thing here? You got to be a little careful, right? This being true, so let's say we've taken the derivative of a function. We plugged in a number C and got 0. Hooray! This does not necessarily mean there's a max or a min. Okay, so if you were to say, look, the derivative is 0, thus there is a max or min, I would say no. That's not true necessarily. It could be there, and if the derivative exists, right, and it's a max or a min, then yes, it will be 0. But, and I know this, the logic of this can kind of be hard because you're so used to, if going one direction, you can go the other direction. Not the way math or logic works. So this only gives us a way to possibly find max or mins. We've got to do more work. So you need to do more work. And we'll talk about how to do that. But it gives us a really awesome way to go find one. Now, the other theorem that's on here, the extreme value theorem, says if you've got a continuous function on a closed interval a to b, so we'll draw a little picture to nail home what I mean there, then f attains an absolute max value somewhere in there and a minimum. And so when you're trying to understand something like this, try to give yourself some pictures. The pictures don't always do it, but it can be helpful. So what do I mean by AB? I mean there's some interval AB, and my function could be defined everywhere, right? It could be like x squared. Sure, that we could be dealing with that function. So I could plug in anything I want to that. But this extreme value theorem is saying, you know what, let's only look here. Only look here. Okay? And if you do that, we can try to draw in a function. So, I'll draw like a simple one to start. Here's a function. Then what this theorem says is that somewhere starting at A, go through B, and you can include those 2 points. Somewhere in there is an x value where you're going to hit your absolute max value and an absolute min. Where could it happen? So let's think about this. And this really informs kind of how you think about the steps that you take when dealing with a problem, like the one we would use for this with this theorem. So what are the options? So a max or min happens, so option number 1, the absolute max min happens at A or B. So these endpoints could be the max or min, which is this picture right here, right? B is the max, A is the min. Or the max min happen not at A or B, inside. So open AB. It happens somewhere in here. And so whenever you're dealing with a problem where you've got a function, it's defined on this range, A to B, included, then if you're looking for a max or a min, first this theorem tells you you will find one. These types of theorems don't tell you how, they just tell you there will be something. It's an existence theorem. It says, look at me, I'm a theorem that says you can find it. And then you're sitting there waiting like, all right, tell me how. And it says, I don't do that. I just told you could do it. You've got to figure out how to do it. We don't always like these theorems that much, but they are very helpful. So this situation is what we're going to be thinking about here. If we've got an A to B, not the whole, possible domain, just a fixed domain, A to B, we look at the endpoints to see what happens. We look inside, which we're going to talk about how do we find the max or mins inside. Well, we've got Fermat's theorem for that. And so it's almost like 2 problems. Check the endpoints, what's happening in the middle. Okay? So we'll talk about that a little bit more later. So we've got the extreme value theorem helping us learn about max or mins. We've got Fermat's theorem helping us find a way to try to find them, which is awesome. And then we've got another definition here, a critical number, and it's just a fancy definition for what we just talked about. A critical number of a function f is a number c in the domain, an input. So a critical number is an input. Careful here. A critical number is an input to the function such that the derivative is 0 or does not exist. So you're going to be like, what? Why? Who cares about that? Well, go back to what we just talked about above. These are the 2 scenarios that are going to help me find max and mins. If your function has a maximum or minimum, local or otherwise, you've got to look for the derivative being 0. You've got to look for the derivative not existing. Those are the 2 places you look. Unless we're in this scenario and you look at the endpoints to see. But if you're not in this scenario where the endpoints could be it, you're in the middle here, the only places inside that you could have a max or a min are going to be where the derivative is 0 or doesn't exist. And just for a picture in your head, because you might not be thinking of it right now, the does not exist one, so like this one, we're just talking about your absolute value of x type functions, where you've got this cusp here. The derivative doesn't exist, but there is a maximum there. So that's why we include that, because we do have those functions where if the derivative doesn't exist somewhere, we could have this type of behavior, which would give us a max in this case. All right, so critical numbers. So what we're going to be doing is we're going to be starting a lot of these problems by saying, what's the critical point, aka the critical number? Go find those. Tell me where my function's derivative is 0 or the derivative doesn't exist. That's where I'm going to be looking for these local max or mins. It just tells me that's where I've got to go. Okay, so, that's helpful. That's pretty nice for us. Okay, and so all of what we just talked about is wrapped up into this thing called the first derivative test. It says, suppose that c is a critical number of a continuous function f. So stop there. What's a critical number? You got to remember this. Go back. It's okay if you have to go back. I literally just said it 30 seconds ago, but that's fine. A critical number is a function where the derivative is 0 or doesn't exist. So at c, the derivative is 0 or doesn't exist. Okay. A, if the derivative goes from positive to negative there, I've got a maximum. If the derivative goes from negative to positive, minimum. If it does not change sign, so positive then positive, negative then negative, I've got no max or min. Okay, so draw it just immediately. I know I do this for everything, but that's because it works. A, the derivative changes from positive to negative, local maximum. Draw local maximum. Boom, there's a local maximum. Okay, what am I doing over here to the left? I'm increasing. The derivative is positive. Okay, what am I doing after? I'm decreasing. The derivative's negative. Oh, okay. Yeah, that makes sense. B, I'm talking minimum. Okay, here's a minimum. What am I doing to the left? I'm decreasing, aka f prime's negative. What am I doing to the right? Well, I'm increasing, aka the derivative's positive. Did I just misspeak? Now I can't remember. Let's say it anyway, over again. To the left, I'm decreasing, right? I'm decreasing, so my derivative's negative. To the right, I'm increasing, my derivative's positive. So, okay, this is all fitting like the picture in my head. C, what if it doesn't change sign? So, cubics are functions that this happens with. Okay, here will be a possible critical number, right here. This is my critical number. I'm increasing. I hit the critical number, which is this plateau idea. The derivative is 0. But then right as I bump off of that, I'm just increasing again. So no max or min. So pictures, these you get confused. Draw a little parabola. Draw a little parabola. Remind yourself of what needs to be happening. Decrease then increase, increase then decrease. What does that mean? Boom. So what does this kind of mean? This means then, if we want to figure out where there are maxes and mins, we just need to find the critical numbers and then look. Am I increasing then decreasing, decreasing then increasing, or staying the same on both sides? If I can figure that out by plugging into the derivative, having a table, looking at a picture of it, oh, that's fine. I can figure out and tell you, yep, max here, min here, nope, neither here. So there we go. That's it, all put together. Okay, and then the next piece connects back to concavity, which remember was the second derivative. So just to remind us, a function or its graph is called concave up if f prime is increasing there. It's concave down if f prime is decreasing. And so this is what got us all, right? All tricky. We've got f prime, and we had that f prime prime. This is going to be concave up if the derivative is increasing. Not positive, negative, increasing. The derivative itself is going up there. This will then be positive. And then you got to remember, right? This seems like a lot to remember, but you could just focus on these two. Just forget about f for a second. Block that out. This function, I take its derivative, I see positive, oh, it's increasing. Then you can just jump back to f to get concavity. So don't forget that, you can take each of these one step at a time. Look function to function. You don't have to have all three in your head all at once. Okay? But altogether, what we can do with this is what's given here in the concavity test. If we take the second derivative and see that it's positive for some x values, then the graph of f is concave up. So if you want to know where a graph f is concave up, take its second derivative, make it positive, you're done. You want to know when it's concave down? Second derivative, where's that negative? Done. That's it. So just to recap, first derivative, where that is positive, my function's increasing. Where the first derivative is negative, my function's decreasing. Where the second derivative is positive, I'm concave up. Where the second derivative is negative, I'm concave down. So it's definitely a lot to remember, but that's one of these things. You just got to practice it. Okay? So that's the concavity test. All right, so we have another test called the second derivative test, and it is just a melding of the previous two. It's not a new thing, it's the melding of the previous two. And again, what am I going to tell you to do? Draw a picture. So suppose the second derivative is continuous near C. Okay? So then if the first derivative is 0, aka we're at a critical point, right? A critical number. Okay, so we're at a critical number, and the second derivative is positive, we have a minimum. Whoa. Okay, so let me just draw something that has a minimum. Okay, well, at this point, we'll call this C, the x value of this C, right? All right, well, the derivative is 0 here. Got it, because we've already talked about there's a minimum here. The derivative, if it exists, is 0. Cool. And then the second derivative is greater than 0. Wasn't that concave up? Oh, yeah, look at this. Bowl up. Oh, so, okay. If I have a critical point and I bowl up there, then I'm immediately telling you it's a minimum. Do the other picture. This little cup down. Here's my critical point. Okay, I figured out this is a critical point, however I did it. Set the first derivative equal to 0. Great. Oh, by the way, I'm also concave down through that whole region. Maximum. Done. Because it's this picture. It might not be exactly this picture, but it looks similar to this picture. So that's it. The second derivative test is these two pictures. The first derivative test, let's go back up, is these three pictures. That's it. That's all you got to remember. We've got 5 total pictures. And if you can remember those, then you can get a feel for what each of these things means and how to use them. That's it. So these are the ideas of this section, okay? All right. So, there's a little bit more we can talk about with concavity itself. So just a reminder, since we're talking about concavity, we want to also discuss sometimes when concavity changes, and that happens at a point of inflection. So that's me saying, right, okay, where give me the second derivative, plug into some number here, some number makes this 0 or does not exist, then I'm thinking to myself, okay, we're looking at a point of inflection here. We got to check it out. So it mirrors the critical points, right? Critical points, possible mins, maxes, you go look at the first derivative. Inflection points, you got to look at the second derivative. So it's just same idea, different derivative. Okay. So there is one extra thing here. I know this is a lot so far, and we'll do this one big example where we're piecing all these together. But I just have to bring back, right, that the previous theorem that has us have to deal with a closed interval. So just to remind you again, because things are a little bit different, right? So the closed interval method is a method we have in a specific type of problem. So there are usually 2 types of problems you have here. Type 1 is you're looking at a function defined on its entire domain. So the entire domain, which usually is not of the form just a to b. It could be all real numbers. It could be from 0 not included to infinity, like log. It could be a lot of different things, but specifically it's not this. then everything we did above works. You just use all those methods. 2 is we are looking at specifically a domain like this, where we have a function that's defined, that could be defined for all real numbers or just a bigger set of numbers, and we are zoomed into one specific interval, a to b. So 1, we use the step above. 2, we got to do this, and it's what we talked about in that picture above. You just do it in 2 steps, right? Here are the 2 steps that you're going to do it in. And I'll draw a little picture for you to kind of illustrate this. Here's A, here's B. So A is going to go up like this, and then like this. Okay. So let's say this is our function. So step 1, find the values of f at the critical numbers of f in a to b. What does that mean? It means give me all the possible local maxes and mins. Here's one. Here's one. So this is step 1 in green. Go find those and tell me actually what the values of f are there. Okay? Then you write that list of numbers down, right? So you would write down this value and the y value, this x value and the y value there. Then you just say, okay, well, what about the endpoints? Like, check these. What's the y value here and the y value here? So you've got these list of y values. 1, 2, 3, 4 in this example. Okay, so then what's the absolute maximum going to be? Well, it's going to be the biggest number on your list, which happens to be this one. This would be the absolute max. And what's the absolute min going to be? Well, it's going to be this one, because this is the smallest y value. Again, y value is what we care about. This is going to be absolute min. These 2 points were local max and mins, and this one was not quite as high as this. This one was not quite as low as that. So they're local, but not overall in here, maximums. So there you go. That's it. It's just this extra step of, okay, you found your max and mins using the derivatives, all that stuff. Yippee. Check the endpoints too. You're done. So it's just like an extra step you have to do. And it's usually not too bad, especially because this inside piece isn't bad. Okay, so we've got this ginormous example here. And what we're going to do is we're going to go through and just power through this, all calculus, all algebra. I'm not looking at a single picture. And then what we're going to do is look at the actual graph, okay, and see what's going on. Try to see if we can use the graph to come to the same conclusions and kind of figure out what's going on with this. So let's check this out. We've got this function, x to the 4th minus 2x squared plus 3. Step 1 here says find the critical numbers. Okay, so what do? I say, all right, critical numbers. Here we go. I can do this. So critical numbers, remember, are when f prime is 0 or undefined. Okay. So in either of these cases, I've got to find the derivative. Okay, I can do that. Well, f prime of x, and this is how all these problems always start, 4x cubed minus 4x. Now this is a polynomial, so it's differentiable everywhere. We immediately do not have to deal with this. The only thing we have to deal with is when it's 0. So that's going to be 4x cubed minus x equals 0. So we got to get our algebra. I think like hat is what you'd say. I don't know why I almost just said shoes. Get your algebra shoes on, whatever those look like. Factor out an x. X squared minus 1 equals 0. So this is going to factor into, take out the x. Don't forget our 4. And you're going to have this left. And so what's going to end up happening, this needs to equal 0. So x equals 0. And then separately, this needs to equal 0. So 4x squared minus 4 is 0. You can factor or move stuff over, whatever you want, but you're going to end up getting 4x squared equals 4. x squared is 1, and so x equals plus or minus 1. Okay, so critical values. I've got 3 of them. Hey, look, this is a cubic. Hint, hint, wink, wink. So altogether, critical values, I've got x equals 0, 1, and negative 1. Woohoo! First piece done. Second piece, tell me where I'm increasing and decreasing this function. Again, no cheating, no looking at the graph, nothing there. Just calculus and algebra. Here's how we do this. And you don't have to do it like this, but I like this method. So we've got 0, we've got 1. Okay. Here's what we're going to do, and I'm going to convince you why this works after we do it. So plug a number in over here. So basically, what I'm going to try to convince you of is these critical values will split us. This whole range of numbers I could plug in, it's going to split it into chunks. There's a chunk here, 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 here. So 1, 2, 3, 4 distinct, not connected chunks. What my claim is that the function is doing the same thing, increase or decrease, in this whole chunk. It could be doing something different in this whole chunk, this chunk, this chunk. Okay? So all we have to do is figure out at any point in these chunks, figure out just a single point. What is the function doing? You know the entire chunk here. Okay, so let's do test points. So what we can do is we can test some points here. So let's test a point 2. So how do I test it? Take the derivative, right, and plug in 2. So f prime of 2 is 4 times, and actually we can factor this. It might be a little bit easier to factor this. Let's factor first and then use this. 4x, so I'm just continuing this factoring, x squared minus 1. So okay, f prime of 2 is 4 times 2 times 4 minus 1. So that's 8 times 3. 8 times 3, okay, that's 24. Oops. 24, which is positive. So at 2, I'm increasing. My function f is increasing, which means it's increasing at 3 and 4 and 5 and 6 and 1.5 and 2.15213, blah, 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 blah. All in here, it's increasing. So then we just go through and we test more points. So you could pick whatever point you want here, but try to be nice to yourself. So 1/2. So all we got to do is test f prime of 1/2. Okay, that's going to be 4 times 1/2. 1/2 squared is 1/4 minus 1. And here's the thing. This is the nice thing about this. You don't even need the number. Who cares about that? Is it positive? Is it negative? Positive, positive, negative. This is negative. You could plug that in the calculator if you want, but you don't even need to. Negative. I am decreasing. The function is decreasing. Everywhere between 0 and 1, not included. Keep going. Just keep going. So now let's try negative 1/2. F prime of negative 1/2 is, okay, 4 times negative 1/2. Negative 1/2 squared is still just 1/4. Positive, negative, negative. I'm increasing. Everywhere in here. Okay, let's try the last little zone that we have to get through. And we'll plug in negative 2. F prime of negative 2 is 4 times negative 2. And then we're gonna square that, so it's gonna be 4 minus 1. Okay, positive, negative, positive. I'm decreasing. There you go. That's it. So from negative 1, not including, all the way to the left, all the way to negative infinity, I'm decreasing. Between negative 1 and 0, my function's going up. Between 0 and 1, the function's going down. After 1, I'm going up. Okay? And if you want to try to think through why this is happening a little bit, you ask yourself this question. Like, let's say you don't believe that this is true, that this works this way. Okay, so let's just, for the sake of argument, say you agree that at -1/2 I'm increasing, but you think that there's another point in here where I'm decreasing. Well, here's the idea. If you're going to go from increasing to decreasing, okay, then you had to pass a point where you stopped moving. So let me say that again. If you were increasing here, and then in this same little zone, you went to decreasing, that would have meant that there would have been some point in between where the derivative is 0. But I know the derivative is 0 only here, here, and here. So that's not possible. Squashed. Argument squashed. So it has to work this way because the only points where the derivative is 0, boom, boom, boom. So those are the only points where things can change. So that forces everything to have to be the same here, same here, same here, same here. Done. Okay, so that's kind of crazy. We just figured out everything about increase, decrease here. So let's write out everything just so we kind of have it, right? Increasing where? Well, in the blue here, -1 to 0, also 1 to infinity, and then decreasing where? We're going to be decreasing -infinity up to -1. That's this purple. Union. And then we're going to be decreasing again 0 to 1. Done. We've got it. We've got our critical numbers. We've got our intervals of increase, decrease. What about local maximum and minimum values, right? Oh, we got to do all this extra work, right? No. What did we say about these critical values? There's going to be a max or a min there possibly. And the way we test that is by taking each of these and going, what happens to the left? What happens on the right? So, for the local max and min, what are we going to do? We're going to just, right here, we're going to draw out our pictures. This is what a min looks like. This is what a max looks like. Okay? So a min has to be decreasing then increasing. A max has to have been increasing then decreasing. So just go to your picture right here. -1, I'm decrease then increase. Well, what's that? Decrease then increase. Minimum. X equals -1 is a local min. Done. What about 0? I'm increasing and then I flip to decreasing. Increasing then decreasing. X equals 0 is a local max. Done. 1, I'm decreasing then I'm increasing. Decreasing then increasing. X equals -1 is a local min. That's it. I already did all the work, so just got to put it all together. Okay, so what's next? It says find the intervals of concavity and the inflection points. We're just going to do the same process again. It's pretty nice. So we got to give ourselves a little more space. So concavity, we just have to remember, how this connects. Second derivative greater than 0, I'm going concave up. Second derivative less than 0, I'm concave down. And then just remember, second derivative equals 0, my inflection points. Technically, we should also be looking where it's not defined, but again, this is a polynomial, so I can do derivative, 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 differentiable everywhere. So we're not going to even worry about that for this one. Okay, second derivative equals 0 is inflection points. So we're just going to do what we did here, find these important points, and then see what happens around them. So let's grab our first derivative. 4x cubed minus 4x, and then we'll write it down here. So f prime is 4x cubed minus 4x. So that tells me the second derivative is 12x squared minus 4. Now, find your inflection points. Your inflection, double I. What's going on there? Inflection points Okay, so that's 12x squared minus 4 is 0. Again, we don't have to worry for a polynomial about does not exist. Okay, and now you can factor this, you can solve just by moving stuff, it doesn't really matter. So we'll just move stuff over. X squared is 1/3. Okay, x is equal to plus minus square root 1/3. Okay, those are inflection points. So then how do you kind of deal with concavity and what to do now? Just draw out your line again. Here is the positive square root of 1/3. Here is the negative square root of 1/3. So that gives me 3 regions here. 1, 2, 3. 1, 2, 3 regions. Test points. Easiest one to test, 0. Okay, what do I do here to test this? I take the second derivative, I plug in 0. That's right up here, right? We just took this derivative. That's going to be 0 minus 4 is negative 4. So that's a negative sign. What does that mean? Concave down. So this is going to be concave. You can use a minus symbol if you still want. I could imagine, though, maybe when you're doing this, having 2 of these diagrams, if it's not really labeled well, with the pluses and minuses, maybe being confusing. So you do whatever you want when you're working on this yourself. If you want to write out the words plus minus down here, still, it doesn't matter. So I'm concave down there because my second derivative was negative. All right, let's try another point over here. Now, square root of negative 1/3, you might be like, oh, what's that number going to be? It's small. You can plug it in your calculator to check. But let's just plug in negative 1 because that's going to be more to the left than negative square root of 1/3. So let's try. F double prime, negative 1. That's 12 times negative 1 squared minus 4. Okay. Again, you just need positive, negative, but we'll just do it out. That becomes a 1, so this is 8. So this whole region is concave up. That's the word I was looking for, region before. I kept using the word chunk. I would definitely take off points from my own written homework if I used the word chunk. Region. These are regions. Okay, let's test 1 here. F double prime of 1 is, well, it's actually also just 8, right? 12 times 1 squared minus 4 is 8. Concave up. Okay, so what are my intervals of concavity? Let's write that out. Interval of concavity. Z. All right, well, I'm concave up from negative infinity up to, and then I stop here, negative, boom. Okay, and then I'm also concave up from positive root 1/3 to infinity, and I'm concave down from negative root 1/3, okay, and then up to positive root 1/3. Boom, done. There you go. That's it. All right, boom, 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 boom. Okay, so the next thing that we might want to do is look at the graph. And so we're going to do that in Mathematica. Now, I was just going to, print them out and show you. So if you want to just skip through this part of the video, go for it. That's totally fine. But every once in a while, just kind of doing the Mathematica in the video is nice. So feel free to skip this until the end where I compare the two. But if you want, you can watch me kind of go through and just off the cuff, how would I be doing this in Mathematica as I'm working through a problem. So, all right, I'm over here in Mathematica. Now, the first thing I'm going to do is define my function. Well, that's nice and zoomed in. Awesome. So that's x to the 4th. Now, again, kind of just like going through some of this stuff. I'm using keyboard shortcuts for this. So Control 6 gives me that pop up to the 4th. Minus 2x, Control 6 gives me the square quick, plus 3. I mentioned this in the intro video, but just to kind of show you again, there's these little keyboard shortcuts that if you're doing this enough, it's nice to know. Like Control and then / gives you a division sign. Control 2 gives you a square root. Those are just so nice to be able to kind of have. And there's a ton more for a bunch of stuff, but those are the ones I use the most. So all right, let's pop that in. All right, and then let's just plot. So let's plot f of x. Okay, and then where am I going to plot it? Well, I've already done a bunch of this work, so I know there's important points here, right? -1, 0, 1, and then these square roots. So just to kind of make sure I have it all, let's do -5 to 5. And we can, see if we like the picture or not. Okay, yep, that's a fine picture, just to kind of like see what's happening. Although, what did we say? We said that there were local max and mins, but it's kind of hard to see that in here. So let's actually zoom in a little more. Aha! Look at that. So by having the wrong starting window, we got the wrong picture there. But which can happen when you're graphing, right? But look, the math saved us because the math told us, no, you really should have a max and min, which, look, just immediately, min, max, min. What did we say? Min, max, min. Nailed it. Okay, well, we're flying high now. So what else? Well, we're supposed to also have points of inflection. Now, it's a little hard to see here, but I think hopefully if you kind of, get close to the screen, really peer in here, it looks like concave up, and then it doesn't look like it does switch somewhere in here. I'm concave down, and then I switch back to concave up. So it does look like there's inflection points there. Okay. Now, what could we do to try to investigate that graphically? Well, here's what we can do. Let's do the second derivative on that same range, x from -2 to 2. Okay, now, what needs to be happening here? An inflection point, remember, was when the second derivative was 0. Boom, boom. Okay, so there's definitely these inflection points in here. I'm concave down in between. I'm concave up here, concave up here. Now, I know I'm pointing at the function and saying concave up, but what you need to be thinking about is when I'm looking at this and saying my function is going to be concave up, I'm talking about this function. This function will be concave up because these numbers are all bigger than 0. Here, the value of f double prime, again, f double prime here, the value of this function is negative. So I'm concave down here. And so that's the connection I'm going back and forth making. So, okay, cool. This is working out pretty well, right? All right, so then Mathematica can do more for us, though, because Mathematica can do the work we did also. So Mathematica has a bunch of different functionality that it can do. So one of them is solve. And, the nice thing, remember, about Mathematica is you just need to know kind of like what's going on. Solve attempts to solve the system of expressions in the given variables. So, okay, well, what do I want? Critical points. Give me this equals 0 in x. -1, 0, 1. Awesome. This is a double equal sign. Red alert. Double equals here. This is common in lots of different coding languages. Regular equals sign is you telling Mathematica, hey Mathematica, I want you to remember what I'm about to write here. Okay? This thing I want to assign the value to this one. Double equals is you saying, okay Mathematica, I want this to be interpreted as like an actual math equal sign. We use a double equals for that. So be careful. That's very tricky sometimes. Cool. So it's got those. Well, you're like, duh, I solved those easy. Give me the one that's a little bit, with numbers that's not quite as nice. So we can do that. And would you look at this? The square root of 1/3 and the negative square root. Now, Mathematica ended up taking the square root off the 1, which is fine because that works. But there you go. We could go a step further though, right? Mathematica, of course, we could go a step further because I didn't just get these points, I figured out the actual intervals. So to do an interval, we're not solving anymore, right? We're trying to figure out this inequality. So you can do reduce. This is the reduce method here. So we're going to click this. What does it say? I know this is, well, just kidding. You literally cannot see that. But hopefully you remember, and it's in my original video, you click the little arrows and it pops up. It says reduce the statement that I'm going to do it by solving equations or inequalities. So reduce, okay, I want to do f prime of x greater than 0, and I want to do it in terms of x. Look at that. Where is it increasing? -1 to 0 and bigger than 1. Pew. Mathematica is awesome, obviously. Where am I concave up? Where am I concave up? Massive amount of work. Oh, here. -infinity up to the negative square root here, and then past the square root. So don't forget that this tool is awesome and you can use it to do all these things. You can graph things very quickly to look at the picture. You can have Mathematica help you solve these things as a check. But look, all of our work worked. It's perfect. We got a nice picture here. We know the max, we know the mins, all that good stuff. So, now what do you have to do? Just practice a ton of these problems. Try different functions, exponential functions, log functions, rational functions. Look at examples where, and you're going to have some in the homework, of course, where you'll see things. You want to look at examples where you've got points where it's not differentiable. The derivative doesn't exist, right? So absolute value functions, stuff like that. But I mean, it's not too bad if all the other stuff is good from before. Are your derivatives good? Is your understanding of how a derivative and a function, what's the interplay there? Increasing, what is the derivative doing? Concavity. If that stuff's good, this stuff is just a lot of time-consuming work here and the algebra too. It can be a little bit messy, but that's it. That's the process. So play around. I'll post this as well with this document for you to play around with. We could have gone a lot crazier too here. We could have put dots on these pictures and all that stuff if we really wanted to, but I just kind of wanted to go through and show you, this is literally what I would do if I was in a problem and I was for whatever reason not trusting any of the work I did here. I just plot the derivatives, have Mathematica solve and reduce, and it was quick. So go through problems, check this stuff out. If you have any questions, of course, let me know, and I'll see you in the next video.